Okay. So, can you turn on your camera? So everyone, can you turn on your camera, please? So during the class, please turn on your camera. Okay. So last week, I just recommended you to watch the YouTube link, right? So some students are asking me that one of the YouTube is not generating the sound, so I fixed that problem. And anyway, from today, we will look at the chapter 1, okay, which is the abstraction of the computer architecture. Okay, so as you know that every place we can find the computers, right? So let's skip this part. And also we will learn about the Moore's law in the later. So anyway, we can classify the computer systems into the 4 categories. One is personal computer, PC. So you know that what is this PC, right? Laptop and desktop, so everything. And server computer. So even though we are not familiar with this server computer, but maybe you already know that like a Naver system, Daum, or Google. So these are server systems, and this has high capacity, high performance, high reliability, right? And this is clustered computers. And another one is supercomputer. Like weather forecasting, we are using these supercomputer systems. Okay, right? So high-end scientific and engineering problems, we will use these supercomputers. And last one is embedded computers. Okay, so for instance, home appliance like a refrigerator or TV or cars. This system has computer systems. So even though we cannot see any screens or any keyboard, but it is also computer systems. Okay. So here in the embedded system case, the price and cost and power consumption or heat, these are more important. So anyway, in this class, we are focusing on the performance, okay? Performance, how we can improve the performance, especially focusing on the personal computer, okay? Okay, so this is a trend of computer systems. As you can see that the smartphone is actually growing a lot. It's old period. It's already more than tablet. So tablet means it is including some pad. So it's lower than, and PC. Cell phone, I don't think it's almost distinguished. Disappeared. Okay. So these days the smartphone volume is increasing and almost saturated. Okay, so here maybe you are familiar with some terminology like cloud systems, right? So cloud system like a Google Drive or some Amazon service in that case, or the Microsoft Azure system. So they are providing some service using server systems. Okay. So anyway, what you are learning in this class is we will learn about the translation from high-level language to the low-level language. So from high-level language to the low-level language, which is machine language or assembly language. Assembly or machine language. So maybe you know that C or C++, right? Very simple cases. So unless you know the keyword, simple keyword, and what is plus, what is multiplication, right? So maybe you can read the C code or if statement or for loop. And from the given C code, you will translate to the low-level machine code. So we will learn about this assembly language and also machine language. Okay. So this is the major goal to understand it. In order to translate to the machine, we have to learn about some interface. Interface means that we will learn about some language actually. Okay, so we will learn about the language, which is machine language. Okay, and then we'll learn about how to improve the performance. Before that, we will learn about what parameters are determining the program performance. Okay, so we'll learn about the performance things. And we will also learn about the hardware design to make this processor. Okay. For the parallel process part, we will not cover this part because we don't have enough time to do that. So in chapter 1, you will just learn about some computer architecture. Okay, so overall things. And chapter 2, you will learn about the assembly code and machine language. And also here, you will learn about the translation from high-level language to the low-level machine language. Okay, so we will learn about this part. And then in chapter 3, you will learn about the logic design, which is specifying some AND or gate. So using this gate, you will make a little bit complicated hardware. Okay, and then in chapter 4, which is the last chapter, you will design a processor using simulator. That's our schedule. Okay. So I think we will finish the chapter 1 maybe today. So in the chapter 2, we will spend a lot of time. Also, we will do some lab in the chapter 2. Okay? So if you don't understand the 2, then the later part will be very difficult. So we will spend a lot of time. Okay, so in order to understand the performance, we have to know about the algorithm, language, compiler, processor, memory, and I/O systems. But here we are just focusing on the process part, and memory and I/O system will be covered in the 4th semester. And programming language, we just look at the C language only. Okay. C language, very simple C language. And then for the compiler, you will do the manual compiler, which means that you will translate by yourself. Okay. And for the algorithm part, we will not cover the algorithm. So algorithm is already given. And C code also is given.
上把也输，上把也输了。哦，利亚那把输了，想起来了。
哎，你知道这把利拉跟上把利拉的我一模一样，你知道啥意思吗？
啥呀？
把先锋先锋上豆瓣的第一天我们冲过去了，我操！给人宰了，给先锋先锋抢了。
Okay. If you are turn on the mic, please turn off the mic. Okay, so here there are many things. We will learn about what is Moore's law, some abstraction things, and common case fast, what does it mean, parallelism pipelining prediction. So here we will not cover this parallelism. We will learn about the pipelining, and also we will learn about the prediction and memory part, and the other part is not covered. Okay. So this part in chapter 2, and this part will be chapter 4. Okay. So let me skip, which is not so important. Okay. So when you are making the program, let's look at what is happening. So here you are writing the C code, right? C or C++ code, which is application code. So this is application code. Then what you're doing is you're compile, right? You're compile and link also. So this compiler or some linker is system software, which is related to the systems. So compiler is also system software. Operating system is also system software, right? This class is not covering about this system software part. So anyway, using this system software, your C code is changed to the binary. Binary means it's machine code. And this machine code will be running on the hardware. Okay. So we are focusing on this part mostly. Okay. And also you will do the manual compile. Okay. Okay, so let me briefly introduce the compilation things. So here we have high-level language, C code. Okay, then compiler is generating the another code. So this is called assembly code. Okay, and from this assembly, actually the compiler is normally generated the machine code directly also. Okay. So compiler can generate assembly code, and also compiler can generate machine code, machine language code. Here machine code is just binary, okay? So 0, 0, 1, 0, this is binary. Okay. So currently we don't know what does it mean, right? So binary means it's just binary. We don't know, we cannot understand what this binary means, right? But later you will learn about that. Each assembly code, one line, is corresponding to the one binary. Okay, so this is one-to-one mapping. One-to-one mapping. So from the binary, you can translate to the assembly, and also from the assembly, you can easily translate to the binary machine language. Okay. So learning the machine language means that learning the assembly code is the same thing. So assembly code is just mnemonic representation for human. Okay, so binary case is very hard to read. So this is changed the human readable code, which is assembly code. So anyway, both are the same thing. So assembly language is textual representation of the binary. Okay, hardware actually read binary code. Okay, so we will learn about this part in chapter 2. Okay, so then let's look at what kind of components are existing in the computer systems. The major computer system is, so if we are drawing the computer system, then computer has actually mainly two parts. or three parts. The first one is processor. Processor is main part. Okay. Processor is computing. So it is controlling, computing, and everything. Control and compute. Okay, so control means in C code you're executing if statement, right? Or quote or for. So these are related to control. And compute means we are doing the addition, multiplication, or AND operation. So these are computing operation. And there is another important component in the computer architecture, which is memory. Okay, so every data is existing in the memory. So memory is containing data. And also memory is including instruction. So we will learn about what this instruction is. Okay, so if we are dividing the computer system into two parts, then the computer system is including processor and memory. That's all. Okay, so maybe we need some I/O. I/O is input and output. Okay, so for instance, using this I/O, you can attach keyboard or mouse or screen or storage system. Okay, so except the processor memory, every other things are I/O devices, or graphic card is also I/O devices. So anyway, the basic operation of processor memory is like this. So memory is containing the instruction. Okay, so instruction and also data. What the processor is doing is processor is reading instruction from the memory. So instruction means, for instance, add, addition. Okay, so after reading one instruction, add, then this processor is analyzing this instruction and then reading data from the memory also, and then computing this instruction, which is addition, and there is a result, right? This result is written to the memory again. So that's how the computer system is working. So the computation or computing of or learning the program means processor is interacting with the memory. Okay, so always processor is interacting with memory. That is program execution. Okay. So if you can understand this interaction between process and memory, then almost 100% you are understanding how the computer system is working. Okay. So here for this I/O device, the slide is talking about how many I/O devices are there. Okay, so let me ask, can you write into the chat? So what kind of I/O device do you know? So keyboard, mouse, or screen, or hard disk. Is there any other I/O device? Do you know that? Can you write down into the chatting? Okay, someone is saying that mic, printer. Is there any other? Printer, okay. Any other? Camera, okay. Speaker, right? touch screen, right? Yeah. That's all. That's a network card, right? So there are so many I/O devices, right? There are so many I/O devices. So some I/O devices are for the input, and some I/O devices are for the output device, or some are for input and output also. Okay, so touch screen. I think you can refer the last year YouTube link. Anyway, touch screen can be divided into the two parts: resistive and capacitive. Okay, so resistive is like this old one. If we are press the screen, then the touch screen is working. For instance, if you are going to the ATM machine, in that case, when you're touching the screen, you have to press, right? You have to give it some press. So, and also ATM machine case, it is not supporting the 2 fingers or 3 fingers, right? Multi-finger is not supported. So that is resistive. So here in this case is pressing the screen that is detecting the touch. So resistive is cheaper than capacitive. Capacitive is your smartphone, right? Smartphone or your laptop. So here, this is supporting the multiple fingers, right? So you are just simply touching it, then is it detecting? So these days, the capacitive type is more popular than the resistive type. But however, the resistive type is cheaper than the capacitive type. Okay. So you're already familiar with this part. And screen part. Do you know what is a CRT display? Brown tube, the old TV, right? So maybe I think LCD is already appeared 20 years ago. So maybe you don't have any chance to look at this CRT. Maybe you can find this CRT in the museum. But anyway, if you are looking at the screen, if you are look at the screen closely, then there is some small rectangle, right? So this rectangle is called pixel. This is pixel. Maybe you heard about the full HD or HD or 4K, right? Or which is actually UHD. So that means full HD and HD 4K, that means is this depending on the number of pixels. So you already know that this one is related to the resolution, right? So for HD case, how many columns and how many rows? Do you know that for HD? Yeah. So 1090/20 and 1080. So almost 2000 by 1000, which is 2 megapixels. Okay. So number of column is 2000 and number of rows are 1000. What of the 4K HD? How many columns and how many rows? So 4K, yeah, 4 means it is the number of column is 4,000. Okay, so it's 4,000. So actually it's not exactly 4,000, it is multiplied by 2, which is 3840. So it's almost 4K, right? 4,000. And this is doubled. So this is 4,000, 2,000, which is 8 megapixels. Okay. So then maybe you can estimate it for 8K, which is almost 8K by 2K, right? So this is a resolution. And also there is some explanation about the RGB part. Let me skip this part. So if you are interested in the RGB representation, then just look at the last year YouTube link. Okay, so let's disassemble the iPad. Okay, so this is iPad. Okay, so here, this is a screen. Right? Okay. This is, what do you think? What is this? This is, yeah, battery. This is battery. Then can you find any processor, memory, or computer systems here? So computer system is this one. These are computer systems. So if you have disassembled iPad, most part is actually battery. So battery is the heaviest one. And the next one is the screen. And the computer system itself is very small. So that's all. This is the computer systems. If we are looking at this one, then here you can find some chip, right? So this is processor. Okay. And also, maybe this is storage. And you can find some place, memory. Okay, so there is some memory here. I don't know where is it. So memory is not far from the processor. Okay, so in this class, we are only looking at this process part. Okay, if we are looking at the processor, then processor has processor is performing two parts. One is computation part, and the other one is control. Okay, so computation part means that it is doing the computation, like a plus, addition, subtraction, multiplication, and etc. Control part means it is changing the control. So you are executing the C code. Sometimes you have to do if statement, where you have to do for loops, right? So this is related to if statement, or go to, or function call, or for loop, or while loop. So related with the program control, that is called control part. Okay. So we will look at this part later. Okay. And also cache. We are skipping over this cache part. So okay, so anyway, let's look at the processor. So this is Apple 851. So here, there you can find the core, right? So you can find ARM core. So here, in this case, there are two cores. This is two-core, dual-core machine. Dual-core machine. So this core is actually a separated processor. So this is also processor, and this is another processor. So each core can execute a different program independently. And you can find some DDL SD RAM interface. So this using this interface, the memory is connected. So memory is connected using this interface. Okay. And this data path, process data path, is doing the addition, multiplication, or some operations. Okay. So we'll look at what this means. Okay. Later. So anyway, if we are looking at the processor, then there are cores and also data part and some other part. Okay. So anyway, you will design this hardware from this class. Okay, so let's look at some big picture of this class. Actually, learning all the detail is very difficult, right? So learning about the every details is too difficult. So we'll do some abstraction. So we'll do some abstraction, and then we will learn about the instruction set architecture. So that is actually the main topic of chapter 2. Instruction set architecture. Instruction set architecture means that it's like a keyword. So for instance, in C code, this one, what this symbol means. So in C code, you are writing this kind of code, right? What does it mean? It's addition, right? Just addition. What this means? This is addition. The next one is bit end operation. Right? So why? Because we make some agreement for this one. Right? So this is keyword. We are defining, okay, so this symbol means this addition, and this symbol means an operation, and also the destination should be placed in the left part, and the first one and second one is source variables, right? So we are making this kind of agreement. Similarly, we will make this kind of representation. For instance, we are making this representation at A, B, C, right? Or and A, B, C. We can make this kind of representation. So these are called instruction set architecture. So we can define this kind of format, okay? So this is format. Okay. So making format is actually making the instruction set. Okay. So instruction set architecture means it is supporting this kind of instruction set. And then we know about the binary and how to implement. Okay. So here, this is chapter 2. And also this is chapter 2. And this one is chapter 4. Okay, so that's our plan. Okay. So there's a non-volatile memory. So memory is volatile, right? Volatile means if you are turning off the power, then the content is disappearing. Okay, so when power is off, then we are losing everything, losing stored data or instruction, everything is gone. So in that case, we are saying this is volatile. And non-volatile is the opposite. It's a storage system. So even though you turn off, the content is still remaining in the storage system. Okay, magnetic disk, which is hard disk. Flash memory based on the flash memory, flash NAND, SSD. Optical disk. These days, the CD-ROM is not popular, right? Do you have a CD-ROM player, CD player, or DVD player? Maybe it's hard to find, or Blu-ray. Okay, so it's almost gone. So here, this is a DVD player. Okay. Network. This is AP, right? Network access pointer. There is Ethernet, Wi-Fi, so LAN, WAN, Wi-Fi, Bluetooth. So there are many network interfaces. Okay. So anyway, we are not talking about this network part in this class too much. Anyway, let's look at the technology trend. So originally, so 70 years ago, using the vacuum tube, it is kind of a switch. So using this vacuum tube, we can make logics, and also we can make computer systems. So using this vacuum tube, the first computer is built, right? Which is ENIAC. Maybe you learn about this ENIAC in the computer history. So ENIAC using this vacuum tube, okay? And 15 years later, transistor was invented. So transistor is more reliable and it is consuming less power. And 10 years later, transistor case only one switch is existing per materials, and integrated circuit, which means that within one chip, there are many transistors. And then 20 years later, so actually this keep evolving. Many transistors are inside, right? So these days, if you're looking at one chip, then the number of gate or number of transistors is more than million, right? Or 10 million or 100 million. So million gates, million transistor existing per chip. Okay, so let's look at the semiconductor. What is semiconductor? You know the conductor, right? And insulator. So conductor case, the current can be passing, and insulator, the current cannot be moved, right? Moving. So conductor and insulator. So semiconductor case, it is a little bit between conductor and insulator. If you are doping some materials, then sometimes it is conductor, or in some condition, it looks like a insulator. So using this semiconductor, we can make a switch. Okay. So let's look at how we can make this switch. Okay, so anyway, let's look at how we can make this integrated circuit IC. Integrated circuit. Okay. So silicon. Where you can find the silicon? What is silicon? So do you remember the periodic table? The first one is hydrogen, right? And then helium. And what's the law of the hydrogen? It's the lithium, right? And next one, helium. B, and then what is it? I don't remember. Please help. Yeah, carbon. And then what's the next one? Yeah, nitrogen and oxygen, fluor, and then yeah, neon. Okay, and then what's the below of the lithium? Yeah, natrium, and magnesium. Okay, and then aluminum. Okay, and then and then what is it? Okay, yeah. And this here, what is it? Yeah. So anyway, here you can find the silicon, right? In Korean, it's a gyuso, right? So where you can find this silicon? So where is a common place to find the silicon? So silicon, you can easily find in the sand, SiO2, which is just sand, right? In the beach, on the beach. You can find a lot of silicons, right? So from this sand, you can extract silicon only. And then making some lump, which is called ingot. It's a pure silicon. Okay, so this is a silicon ingot. It looks like a black. It's black. Then this is a silicon ingot. Then the machine is slicing this one. Okay, slicing. So slicing. Then each one called wafer. Okay, so each slicing is called wafer. So making this wafer, then from in this wafer, there are many steps. So for this wafer, it is doping something, and then giving some patterns, masking, using some light, using the mask. So it has some mask here. Okay, and then etching. So many, using the many steps, and finally it has patterned wafer. So the processing is completed. Then for this wafer, it is testing. Okay, so this is working, or this is working, or this is working. They are testing. So after testing, then maybe something is working and someone is not working. Okay, so this is not working. So it's not work. Then it is slicing everything. Okay, slicing. Then so each rectangle, this one is called die. Okay, so it's testing each die. And for each die, it is doing the packaging. Packaging means using like a plastic or some another materials. It is protecting this die. And also here there is some leg and is interconnecting to this leg. And then cover this one. Then this is, after packing, it is kind of chip, okay? That's a chip. After making the package, and then it's testing again. And finally, shipping this chip to the customer. Okay. So from the silicon ingot, the final chip. So for instance, here the one from the one wafer, the number of working chip is depending on the process. So the processing was differencing. So anyway, maybe here there are 100 die per wafers, but after testing, finally 70 chips are working. Then we are saying that the successful rate, which is called yield. Yield is a successful rate from the one wafer. From 100 die, only 70 is working, then yield is 70%. Okay. So if yield is high, then the company can make more working chip from the one wafer. So they can make more money. Okay. So for each company, each semiconductor company has different yield. So yield is kind of private information for each company. So like if they are making one DRAM, some company has yield like 90%, one other one is like a 45%. Then this company A can drop price to half compared with the company B. They can make a double number of chips from the one wafer. Okay, so this is Intel Core i7 wafer. You can see that here, these small things, right? So this is not going to be used. We cannot use because, so we cannot use this part, right? This part only, maybe we can use here, this one. Okay. So here, this case, the diameter is 300 millimeter, which is 30 centimeter. So one wafer size is a 30 centimeter diameter. And it is using the 32 nanotechnology. 32 nano means that here there's a lines, right? There's a pattern. The pattern, the line width is 32 nanometer. So these days, the modern technology, like from the TSMC or Samsung, they are supporting the 5 nanometer technology for making one lines in the chip. If the line width is getting narrow, then more chips we can make from one wafer. Okay. And this is yield. So yield is just simply, you can think that from one wafer can make 100 die. From that, only 65 die is working, then the yield is 65%. So that's the definition of yield. Okay. So how many are generate successfully working? That is yield. So let me skip this part, the detailed part. And we have to define the performance of the processor. So there are so many ways to define the performance. So for instance, let's think about the airplane, 777, 747, Concorde, Douglas, DC-8. So there are many airplanes. So passenger capacity case, 747 can support more range, the Douglas DC, and cruising speed, Concorde is the fastest, and passenger with the speed, then 747 is best. So from these figures, which airplane has the best performance, do you think? Do you think which is the best airplane? It is really difficult, right? Because we didn't define the performance. So without definition, we cannot define, without definition, we cannot determine the performance, right? So in order to talk about the performance of processor, we have to define the performance first. Okay. So we have to define the performance of the computer system first. So there are two metrics are existing: response time and throughput. So response time means, for instance, you are clicking your program, that is computing and generating the output. So that time, so response time is actually time. So how long it takes to do the task after you're pressing the button, how many times are taking to complete it. Throughput is, so this is the response time is normally used in the personal computer case or your smartphone case. Throughput is per unit time, how much work can be done. So per second, like 100 program can be executed. Then the throughput is 1,000. If 1,000 program can be finished per second. So this is useful for the server machine. Server case, there are so many requests come to the server simultaneously. Okay. So these two, response time and throughput, are normally regarded as a performance. And this response time and throughput are affected by how fast processors is used, or how many processors are used, depending on. So if we are using the fast processor, then the response time generally improved. Right? The response time is improved. If we are adding more processor, then throughput is improved. So definitely, if we are using the faster processor, then throughput is also improved, right? So always faster processor can improve response time and also throughput. So anyway, from this class, we will focus on the response time. Okay. So how we can reduce the response time. So that is performance of the processor. Okay, so let's look at some example, relative performance. Let's look at example. Okay, we are running same program on machine A and machine B. Okay, two processors are existing. A case, it takes 10 seconds, and B case, it takes 15 seconds. So which is faster between A and B? So definitely A is faster. How much faster? A is faster. How much? Yeah. 50% more faster, right? So we can simply say that it was 10 seconds, now it is 15, so 1.5 faster. So 1.5 times faster than B, right? 50% more faster. So 1.5 times faster than B. So that's a lot of performance. Okay, so the other part, measuring the execution time and clock time, and the other part we will continue on the Wednesday. Okay, so Wednesday we can finish this measurement thing, and then we are going to the chapter 2 directly. Okay. Any question? Nothing. Okay. Then, yeah. See you on Wednesday. Okay. Yeah. Bye.